C1 and C2 are curves obtained by intersecting y equals y0 and x equals x0 with the surface S. Point P lies on both C1 and C2, and thus T1 and T2 are tangent lines to C1 and C2 at this point P. The tangent plane is then defined by a plane containing both T1 and T2. The plane passing through point P has the equation of the form shown here. If we divide through by c and let little a equal negative a over c and little b equal negative b over c, we then obtain this new equation of this form. This equation is the tangent plane at point P. The intersection with the plane y equals y0 is tangent 1, and the intersection with the plane x equals x0 is tangent T2. By compiling this information, we obtain the formula for a tangent plane at point P to surface S. To find the equation of the plane tangent to the surface z equals x cubed y cubed plus 2y at the point 1, negative 2, 12, we take first the partial derivative with respect to x and then with respect to y, sub in the point, and plug it into our formula.
A linear approximation is an approximation of a general function using a linear equation. It uses the tangent line as an approximation of the curve near the point where the tangent line touches the curve. Therefore, the closer it is to the point, the more accurate the value is going to be. This is used to find the value at a point on the function that would normally be difficult to calculate. First, find the partial derivatives f of x, f of y, and f of z. Then, find them at the point 6, 3, 2. You can then use these values to find the linear approximation.
For a function of one variable, dx is defined as an independent variable and dy depends on x in the following way. dy equals the partial derivative of f with respect to x times dx. For a function of two variables, dx and dy are defined as independent variables and dz depends on both dx and dy in the following way. dx equals the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. The independent variables listed above are called differentials, and the dependent variable, dy for one variable and dz for two, are called total differentials. df can also be used to replace the notation of the total differential. Since the formula for a linear approximation is as shown here, if we substitute in the formula for the multivariable differential, we get the following. Here is an application example. The dimensions of a cylinder are height is 50 centimeters plus or minus 0.1 centimeter, and the radius is 5 centimeters plus or minus 0.2 centimeters. So given these parameters, to estimate the largest possible error when calculating the volume, we do the following. We use dV as the difference in volume, and this will be our approximate error. So writing down the formula for dV, and then we insert the partial derivatives as shown. So since the absolute value of the radius, or the change in radius, is less than 0.2, and the absolute value of the change in height is less than 0.1, we use the largest possible error, so 0.2 and 0.1 respectively. Plugging these numbers in, we get 322.01 centimeters cubed as our dV. And to ensure that our answer is reasonable, we compare it to the magnitude of the volume. So computing the volume, we get 3,926 centimeters cubed. And then if we divide the potential error by the volume, we get approximately 8%.
The graph shows a function of one variable with a tangent line at A. Here, dx and delta x are shown as equal. However, dy and delta y are not. dy is equal to the change in y from the tangent from A to A plus delta x. Delta y is equal to the change in y of the function from A to A plus delta x. If dx is equal to delta x, which is equal to x minus a, and dy is equal to delta y, which is equal to y minus b, then the formula can also be written as shown.